All right, thanks, Hemant. I would like to start my presentation by just giving introduction to modeling, introduction to Maplesim, and then we're going to actually jump to the Maplesim environment and see the Maplesim model in action. So there are actually three parts that I would like to talk about when it comes to Maplesim. Maplesim is a modeling and simulation tool that you can use to build system-level multi-domain models. You would do this by using components from different libraries, and you can actually build your custom components in Maplesim as well. There are also a few apps that you can use to quickly analyze the model that you've built. On top of that, you have Maple, and as you might know, Maple is both a symbolic and numeric computation environment, and you can connect a Maple worksheet to a Maplesim session, and then you can use the capabilities of Maple in terms of design space, in terms of available packages to do design space exploration and optimization. And finally, Maplesim connector, it's different ways for us to kind of being able to connect Maplesim models to different tools. It can be either through functional mockup interface, FMI standard, which would be the topic of interest for today, or it can be through plain C code. So just an example of using Maplesim in different applications. In robotics, you can use Maple and Maplesim to get equations of your robot, to do inverse kinematics, to analyze the dynamics of your robot, to probably consider the actuation for different joints, and also do control design. In this example, I've used Maple to get the equations, the multi-body equations of the robot, and solve for different variables to do the inverse kinematics so that the robot end effector would follow a predefined path. In automation, you can build a digital twin of your actual machine, and what you can do then is to test your control code against this model, this Maplesim model, and long before you actually have access to the machine itself. And then you can do component sizing and probably analyze the hydraulic or electric actuation. In this example, I've used Maplesim to build a circuit, a hydraulic circuit for a moving platen of an injection molding machine. And finally, in automotive, in our example, we can use Maplesim to do vehicle dynamics to analyze the powertrain of your vehicle. It can include engine, internal combustion engine, electric motor, and battery pack, which we will see an example of this later down the road. And finally, you can also model the driveline of your vehicle. In this case, this screenshot is actually for the model that we're going to examine. So a few relevant libraries to today's example. Driveline has components to model all the way from basic gears to planetary gear sets and actuating the clutches for these gear sets. A few types of clutches, brakes, CVT transmission, engine, differential gears, and components for modeling longitudinal vehicle dynamics. The battery library has a charger and two approaches for modeling batteries. It can be either electrochemical or equivalent circuit, and you can choose between different types of batteries with different chemistries. This library also has two parameter identification apps that you can use to identify the battery parameters based on your experimental data. And then electrical library, a few examples of this library. The electrical library is actually extensive and includes hundreds of components, but a few relevant components would be asynchronous, synchronous DC machines, and or power converters. All right, so at this point, let's just go to the Maplesim environment and talk about the model. So this is the environment. This is the interface. So I will just maximize this. Okay. So the canvas in the middle is workspace for the modeling, and you can see the libraries from different domains on the left. So the hybrid electric vehicle top level includes three main subsystems. You can see the these subsystems are drive cycle, the powertrain, and the vehicle dynamics. Drive cycle is actually a timetable that I've used data points for an arbitrary driving cycle for a vehicle around the track, but you can just use data points for few of the standard driving cycles, such as FTP 75, for example. The powertrain subsystem, you can see the layout here. And starting from the driver block, it actually gets the feedback, vehicle speed feedback, and also the steady speed, and then commands the accelerator and braking pedal positions. It's actually a PID controller that I've used in this model. This block then gets these command positions, and then gets the vehicle speed and compares it to a threshold to figure out if the regenerative braking is available. Then it would generate the torque demand from the powertrain, and the energy management system then gets this demanded torque and distributes the torque among the different components of the powertrain. Just going to the EMS subsystem. I've coded the EMS to actually be a rule-based one. So there are a bunch of different tuning parameters and thresholds on vehicle speed, on the demanded torque, and the SOC, battery state of charge, that then you can tune, and based on few rules, this component will kind of figure out the way to distribute the torque. And I've also coded it to have two operational modes, an eco mode and a sport mode, and we will see how each of these modes will affect the results. These are actually this is actually a custom component. You can generate a component in Maplesim based on your equations, or based on your equations, and it can be either through a Maple worksheet, or it can be through Medallica programming language. In this case, I've used Medallica to make this block. Okay, so on the electrical side, I will double click on this. I've used a nickel metal hydride battery pack. Again, this is coming from our battery library. And I've also used an equivalent circuit approach of modeling it, but you can replace it with any other battery type that makes sense to your application. And then this battery pack powers a permanent magnet motor. And again, this motor comes from the electrical library, and you can swap it with other type of motors that is for your vehicle. The internal combustion engine subsystem, it has an engine which has the maximum torque versus engine speed curve, and then converts the throttle command to the torque. And there's also another lookup table that calculates the fuel flow based on the engine torque and engine speed. You can see in the layout that the electric motor and the engine are connected together in parallel. So this is a parallel hybrid electric vehicle, and they're also connected to the output shaft through a CVT transmission and a final drive. So the ratio of this CVT transmission is controlled by this block here, which based on the brake-specific fuel consumption performance of the engine, controls the ratio of the CVT. I've also captured my parameters in the parameter block, a few parameters like the minimum allowable SOC, or the number of battery cells, and so on. Then I can use these symbolic parameters in different places in my model. For the vehicle dynamics, I'm actually using a longitudinal vehicle dynamics, and this component models a few aspects of vehicle dynamics, like weight transfer between axles, also the vehicle inertia, as well as the loads on the vehicle, like aerodynamic drag or gravitational forces because of the inclination. And the tire components generate the longitudinal force for the vehicle, and you can use either linear or magic formula. The mechanical brakes are connected to the front. The mechanical brake is connected to the front axle, and the output torque from the powertrain is connected to the rear axle. So this is a rear wheel drive. So at this point, when I have the model set up, I can actually run this and simulate this and get and check the results. I have done a simulation before and I saved the results, so let me just open those results. I'm going to focus on the eco mode first, and then we'll compare it to the sport mode. This figure shows the set speed versus the vehicle longitudinal speed. And you can see that the simplistic driver, the PID controller, actually does a fairly good job in following the set speed. And you would see also that the vehicle goes through phases of acceleration and braking, and also kind of keeping a constant speed. This figure shows the output shaft torque. And for instance, you can see for the braking phase, you have actually negative output shaft torque, and that's because of the regenerative braking. So if we take a look at the motor torque, you can see the torque is actually negative, which means that motor is acting as generator and charging the battery pack. And we can see the result of this in the battery SOC plot, which at this phase, the battery pack is getting charged. Also in the braking phase, the regenerative braking works side by side with the mechanical brakes. For the acceleration phases, in the initial time, both the electric motor here and the engine provide positive torque, which means it acts sort of like a torque boost scheme. But after that initial acceleration, then motor torque goes almost to zero. Now I'm going to toggle on the sports mode results, and we will compare it to the eco mode. Okay, so from the output shaft torque, you can see that the powertrain in both of these modes actually provides the same amount of torque, almost similar, but we will see how a different strategy has been used to distribute this torque between the components. So from the motor torque plot, we see that the amount of torque provided by motor is higher for the sport mode to provide that instant feel of acceleration that electric motors are providing, but this comes with a price, and we can see the effect of using excessive use of the motors in the SOC plot, although the eco mode was actually charging the batteries during this 0 to 40 seconds, but the sport mode is actually depleting the battery pack. So as you saw, for the first pass of my analysis, I had used longitudinal vehicle dynamics. But let's see what can be achievable by integrating Maplesim to Adams through FMU, FMI technology, through functional mockup units. And so I want Maplesim to take care of the powertrain model and Adams of the vehicle dynamics, so that I'd be able to run my powertrain against the full-fledged 3D vehicle dynamics model. The integration can go both ways. You can either, from Adams, generate an FMU of your vehicle model, and then in Maplesim, you can bring in that FMU and replace it with this simplistic vehicle longitudinal dynamics model, and then run your powertrain against that component. But and the second approach is that you can, which we're going to talk more about that approach today, is you can actually generate an FMU of the powertrain in Maplesim, and then pass it to the Adams and use that FMU, that powertrain model, to propel your vehicle. So for that, in Maplesim, you would use the FMU generation app. Under apps and templates, I would go to the FMI connector, double click on the FMU generation app, and this will load up the FMU generation app for me. So the app is loading the model now. And what I do next is to select the powertrain that I want to generate an FMU of. So now, once I've loaded the powertrain, I would be able to see inputs and outputs, and also the different parameters that I have in my model. Probably I'm going to keep a few of them in the generated FMU to be able to tune them in the Adams. And I can configure the export options. So just waiting for for the app to load the powertrain subsystem, and we can actually check the inputs and outputs that are associated with the this FMU. So inputs, these are actually the as you saw are the inputs for that subsystem, and are, for example, output shaft speed, the set speed, and vehicle longitudinal speed are the inputs. I have defined a few outputs here to also kind of export with my FMU. I can see different parameters, and I can choose to either substitute them with a numerical value or keep them symbolic to tune it later. And I would be able to define a few my export options. So you can see that you can define the FMI version, the FMI type, either as a model exchange or for co-simulation. You can also choose which solver that you want to embed in the FMU. And this communication step size would be the step size that the Adams model and this FMU will communicate and share or exchange information or signals data. Then I need to define the directory, and finally, I can generate FMU archive, and then I would generate an FMU of the powertrain, and we'll be able to go back to Adams and import it. That at this point, I will let Shankar to talk more about the integration of Maplesim FMU to Adams.
Thank you, Saeed. Hemant, can you? Yep, I got it. Okay. So thank you, Saeed, for explaining all the control strategy for the powertrain inside Maplesim. So now let's look at some of the aspects coming from the Adams side for this workflow. So as Saeed mentioned, this workflow of HEV or even electric powertrains can go both ways. Either you plug in the Adams model as an FMU inside Maplesim, or you use the Maplesim FMU that Saeed just generated and load it inside Adams to kind of see how the different outputs look like, how you can run it inside an Adams track event, or with different configurations of driveline or different configurations of the powertrain inside Adams. So essentially, we are using the FMI approach over here. We use different versions of the Maplesim FMU for different applications, but as a baseline, most of them take a driving torque from Maplesim, which is applied either to the drive shaft or some other part of the Adams template, and in return, Adams returns the vehicle speed and the engine omega. So this is how we develop a co-simulation FMU between Maplesim and Adams, and either it can be run at the Adams environment or inside the Maplesim environment. And you can see different components of the simulation, such as battery state of charge, engine and motor torque, fuel rate, which are outputs of the Maplesim FMU inside Adams. So we'll look a bit more on how this workflow actually happens. So one of the possibilities is to export this FMU block of the Adams plant model, which contains all your vehicle dynamics, chassis dynamics components, and plug it inside the Maplesim environment, which would essentially be driven by a drive cycle inside Maplesim. So this could be any standardized drive cycle that you're looking to test the efficiency of your powertrain system combined with a high fidelity vehicle dynamics model. The other option, which we'll be also exploring today, is to import the FMU that Saeed just generated, bring it in through the Adams controls plugin, and then connect the inputs and outputs and simulate it using a realistic track data set. It could be your customer test track or some other road stretch of highway that you want to evaluate the vehicle performance on. And with this, you get the added benefit of using a high fidelity vehicle model to kind of see how different control strategies, different torques coming into the system actually affect your model performance, how your regenerative braking is affected, how your powertrain efficiency is affected when it is run with a high fidelity full vehicle dynamics model inside Adams. So that's what we'll be looking at today. Before I move to the Adams GUI, we did try to do this with several different configurations of Adams models, which I'll be showing in the Adams interface as well. But as a baseline, we just started with the sedan rear-wheel drive model from the ACAR concept database. which a lot of you might be familiar with. We made changes to the driveline template and got the input from the Maplesim model over here. We changed some of the components in the powertrain so that the powertrain GSE is deactivated, as we'll be using all the inputs of the powertrain coming from the Maplesim model instead of the standard Adams IC engine powertrain. And additionally, depending on the use case, whether the Adams FMU is inside Maplesim, where Maplesim is feeding in a lot of driving signals, we also made modifications to the event. So for example, over here for regen braking and other additional inputs from the drive cycle in Maplesim, we had to make some changes to the event as well, which are reflected in the ADM as well. So as you all know, Adams is quite flexible, so you do have the opportunity to make your own templates. I'll be showing some possible applications with what we currently have. So right now we are just passing in the signal to the drive shaft, but you could move to other configurations such as a dual motor config for EVs or the torque vectoring application as well, depending on what particular HEV or EV workflow you're looking at. So I'll go into the Adams GUI, and we'll also look at how you can import the Maplesim FMU inside Adams or export the Adams FMU to Maplesim. So let me switch to the GUI. So before I move to the actual Adams model, so as you can see over here, my powertrain GSEs have been deactivated. There's nothing much coming from the powertrain because we are getting everything from our Maplesim environment. The driveline torque has been modified so that we receive the inputs from Maplesim. So this is one potential workflow application that we can use. But depending on the kind of HEV or EV vehicle you have, you could have something like this, a dual motor config, where we are sending in the torques to the front motors into the Adams templates. So this is one possible configuration that you have, and you can leverage the power of the Adams templates over here. Similarly, you could have a template for the battery. You could split the torques for the regen braking between the brake subsystems as well. So you could have different configurations of templates based on the workflow you're trying to achieve. And we could definitely support users as they work towards integrating different control strategies into a full-fledged Adams model. So one important aspect of this is that to connect with an external FMU, like we have with Maplesim over here, it's good practice to kind of get a template where you connect the input and output signals. So as you can see over here, we've got all the engine torque, fuel rate, shaft torques, battery SOC coming in from the Maplesim model into the Adams template as well. And this is how we connect the I/O signals. So moving to the full-fledged Adams model, as you can see, we are using the sedan rear-wheel drive for this particular workflow application with the Maplesim HEV powertrain, where we have made changes to the driveline over here. And additionally, we changed the engine template so that there's no powertrain GSE active over here, as we are getting all the values from Maplesim environment. But depending on the application, as I mentioned, you could have a completely different vehicle configuration, having a dual motor config. So depending on the user and the use case that you're trying to achieve, it is surely possible to kind of play with the Adams templates and find the best fit for your application. So a lot of you might already be familiar with the controls plugin option inside Adams. So once you load up the controls plugin, you'll get an option to import or export an external FMU like we have with Maplesim. So if you want to export the Adams FMU, and for controls engineers especially when they are not looking to play around with the model much, they could export an Adams FMU with all the channels that is required for communicating with the Maplesim simulation. So you could export this particular FMU that we have, and it will show up as a FMU component over here. And you could load this inside your Maplesim environment and run it with a Maplesim drive cycle. So that's one example. In this case, you'll be using a target as a FMI standard 2.0, which is what we're currently using. And it will be running using the co-simulation standard inside FMI. Another advantage that you have with this is that for controls engineers who don't really want to play around with the properties of a full-fledged Adams model, they could expose several different parameters of the model, such as the chassis mass or some other properties for the suspension or the steering to see how they influence your controllers and how much effect they have on the HEV performance for this particular workflow. So you could always include those properties inside the FMU that you're going to export from Adams and load into MapleSim. So that is one option that you have. But for this application, what we did is that we imported the MapleSim FMU that we got from Saeed. We brought it into Adams. We set up the signals. And essentially, we set up a communication between them. And once you hit apply, you'll get the equivalent GSE connections for this co-simulation workflow using an FMU. So over here, as Saeed mentioned, we'll be using a communication interval of 1e minus 3, which is how the communication between the two softwares will be happening. So for saving time, I actually ran the simulation already. But as you can see, we are running, instead of, if you ran it inside the MapleSim environment, as Saeed mentioned, you could have your own speed trace or your own track profile, or you could use any of the standardized drive cycles. But if you want to run it on your test track to see how these controllers and how these HEV and EV powertrains work inside an actual test track or an actual road you want to test it with, you could definitely load it up inside Adams and see how a full-fledged multi-body dynamics model works over there. So as I mentioned, you'll be loading up the FMU inside Adams, setting up all the IOs, and these are converted into GSEs inside Adams. Now, another very important aspect is that, as Saeed mentioned, he had an eco and sport mode option inside his FMU that he exported from MapleSim. And there's a very good possibility that some of the multi-body or chassis dynamics engineers who are studying the vehicle or modeling the different components, they wouldn't necessarily want to go in and modify something in the MapleSim environment. So instead, Saeed has embedded certain properties in the MapleSim FMU, which we can also modify from the Adams environment. So as I already created this FMU and made the connections, if I go to my database navigator in Adams, you can see that I have this HEV FMU GSC that has been created. So you can see that we've got some of the parameters that have been exposed inside the MapleSim FMU, and one of them is this HEV powertrain torque splitter, which is essentially one of the control strategy which converts between sport mode and eco mode. So if a MBD user is looking to kind of change some of these control strategies to see how the torques affect the model performance inside Adams, to see the difference in bushing forces or the performance of the vehicle, the battery SoC and different configurations, they can, there are several different ways to do it, but I usually go from the command navigator, I press variable, go to modify, and I choose this GSE variable that we were looking at. And I can select this option over here, and I can change the values which are present in the FMU block from 0, 1, or 2. So right now we have 0 for standard mode and 1 for the performance mode, which essentially changes the control strategy inside the Adams environment. So a user doesn't have to go to the MapleSim environment to kind of change different control strategies. So that is one key advantage where you can import an FMU from MapleSim and toggle through the different controller strategy that has been set up by your controls engineer and run it inside the Adams model. So I already ran a couple of tests with this, and I'll walk through some of those. So as we discussed over here, we were getting the torques from MapleSim, and we ran it across the track. So you can see this animation, hopefully it's coming through. So you can see that as the chassis velocity goes down and the vehicle is braking, your battery SoC is increasing. And these are all the quantities that are coming in from MapleSim. So Adams essentially supplies this target velocity. And based on the event that we're running, it could be a track event, it could be a simple straight line acceleration event. MapleSim would essentially take in the velocity, and the controllers will try to attain the set velocity or the set throttle pedal positions to kind of figure out what the equivalent response would be for the model running on a track, the full-fledged MBD model from Adams. So this gives you a lot of opportunity to study your model in detail, to find out where there can be a lot of noise, resonance, or how the region performance is affected with different control strategies. So those are different options that you have with the Maplesim FMU inside Adams. So looking into the results again, you can see that we have the battery SoC for the sport mode and the standard mode. So as Saeed already mentioned, in the sport mode, we are actually using up a lot of energy. So you can see that the battery is not recharging in this case, running on the Adams event. If I look at the speed and motor torque, you can see that even with the sport mode, we are attaining higher speeds for the same event, and we are also using a greater amount of motor torque over here. You can also see a simple comparison instead of a track event of how when you toggle between control strategies, you see a higher acceleration response, and the vehicle accelerates faster when you move to the sport mode as you're using more of the motor energy over there. And similarly, there is another comparison of the chassis velocities for the track event. So coming from the Adams perspective, you could also study different bushing forces based on the kind of controller strategy that you're trying to run. So this is very important for all your chassis dynamics engineers or your multi-body dynamics engineers to kind of figure out how different control strategies lead to vibrations in the system and also regenerative braking performance, because a lot of the performance of your HEV and EV systems are highly dependent on the rotating inertias of each of these components inside Adams. So you could assume that all these masses, rotating masses, which have been accurately modeled inside Adams, would lead to different responses in the system based on the torque inputs that is coming from a standard configuration or an eco or a sport mode configuration from the Maplesim FMU. You could also toggle off a regen mode. So what I did over here is that instead of sending a brake command, I changed the strategy inside Adams itself to turn off the regenerative braking system. So Maplesim currently is not providing me with any kind of response for regen braking. So you can see that I'm just running the standard mode, but with regen off. So you can see how my vehicle decelerates slower because there is no influence of the regen braking coming over here. And my vehicle also accelerates slower because the motor is not being charged up. The battery is not being charged up. So you could toggle through different strategies inside the Adams environment itself and see how they influence your vehicle performance and your vehicle behavior. You could study different components, different bushing forces to kind of optimize your system. And as you can also see that some of the bushing forces are highly different between the standard and the sports mode. So you could actually study in detail how these different control strategies affect your system. So that is a brief overview of this current workflow that we achieved with Maplesim. As I mentioned before, you could move to a number of other Adams templates, and we could definitely assist you with developing these templates for EV or HEV systems. It could be different configurations of a Maplesim powertrain running inside Adams. They could be having different motor configurations, different battery packs that Saeed explained at the start of this webinar. And looking at the advantages of having a high fidelity Adams model, rotational inertia, as you all know, plays an important role in the performance of the EV and HEV powertrains. They account to about 10 to 13% of the regenerative braking performance. So it is very important to have an accurately modeled full vehicle system over here inside Adams so that you can see the influence of different parts on the control strategies. It's also important to study the rotational inertia influence in gear shift for especially HEV systems. And at times there is a lot of resonance in the model coming in from the EV and HEV powertrain. So it would be good and beneficial to study this inside the Adams environment as well. A lot of, like in the Maplesim environment, you could program your own speed trace from an external track, but a lot of customers already have their pre-built RDF or CRG road formats inside Adams. So you could gauge the performance of your vehicle like an actual test driver would do. In this case, moving to the Adams GUI again, we just simulated everything with the Adams Smart Driver. So you could have your own Adams Smart Driver run with the track of your own choice in either a CRG format or some other format that you might already be using for durability simulations. So you have the opportunity to use the Adams Smart Driver to kind of replicate the kind of use that you would see from a realistic driver or a track driver on your actual test. So those are some of the advantages that you have of leveraging the Maplesim FMU inside Adams. And in addition to that, there are some more benefits of using a parametric FMU when you export it to the Maplesim environment. So a controls engineer who doesn't necessarily care about a lot of these characteristics of the Adams model, they can also move to using a parametric FMU, which we also looked at, where they can expose different parts of the chassis, the suspension to change the mass or some other simplistic properties, and they don't have to necessarily come back to the Adams environment. So they can also use the benefits of parametric FMUs to run it in Maplesim environment to see how the controllers are affected. So that is our workflow for this part of the webinar, and that's all I have. If you have any questions, feel free to ask us. Hemant,
Thanks, Shankar. Thanks, Shankar, and thanks, Saeed, as well. Great presentations. So at this point, if you have any questions on the presented content, please type them either into the chat window or the Q&A window. We have several already, Shankar and Saeed, so let me just start reading this off. So the first question is on the FMI and the FME standard as well. So Saeed, very briefly, can you talk about the FMI standard and what an FMU is?
Sure. So on the FMI standard, it's actually a standard for exchanging the different dynamic systems from different tools. So it's kind of a standard for writing and developing and kind of composing the code in a way that it can be supported by different tools. So in terms of Maplesim, when you hit simulate, what happens is that it goes through the model and gets the equation for your system, and then finally you end up with a set of equations. It's going to be also in a differential algebraic set of equations for your system, and then through FMU technology, what can you do is to actually generate C code based on this, but with an FMI standard, and then it can specify a few different settings for it. For example, in our case, you can also choose a different solver that is kind of makes sense for the system and model you have to be embedded inside the FMU, and then you can exchange your dynamic systems that you have developed in Maplesim to use in a different tool, or you can also do other way around. You can bring in and import the model, the dynamic system that you've developed in a different tool into Maplesim. It depends on what is your focus of interest is. So you can kind of now integrate and work with different tools and also have the capability of integrating them together.
Okay, perfect. Yeah, thanks, Saeed. There's a second question, and I guess this relates to both Saeed and you, Shankar, as well. Probably, Shankar, you can start off. There's a question about the CoSim solver type, right? So maybe the question is, how do you decide on the solver type when you're running these code simulation applications? So any guidance first on the Adams side, and then we can talk to Saeed and talk about the Maplesim, best practices as well.
So from the Adams side, we did investigate different solver settings, and so that's how we decided on a benchmark. But I think for us, the time step was quite important because even the Maplesim model was running in 1E-3, same as the Adams model. And additionally, we did run it with gstiff, HHT, and even the fixed step integrator. And we didn't see a big difference so far. So we haven't, at least from the Adams side, I haven't come across a use case where one solver is not performing better than the other so far for this co-simulation exchange. But essentially running gstiff or HHT would be a good option. So I resorted to gstiff SI2 for this particular application.
Okay. And Saeed, any comments on the Maplesim side on the solver type or solver settings, perhaps?
So once you're developing your Maplesim model, based on the nature of the equations that you're getting, you're gonna do a bit of a study on the solver. So Maplesim has two different types of solvers. It can be either fixed step or variable step, and also there are different solvers available in either of these categories. So what you would do in Maplesim is as you're developing your model, and probably it's getting more advanced, you're also do need to do a bit of a convergence study to see which kinds of these solvers are doing the better performance and also converging to the results that it's kind of reasonable. And then once you're confident with the different tolerances and the settings of your solver, you would use the same settings for the solver while generating FMU, and that solver will be embedded inside your FMU, and then you can just pass it to different tool.
Okay, thank you. And there's a question about the communication rate between the two tools. So any comments? So the specific question is, what was the lower limit for the communication rate?
I don't think we explored one because we just started with 1E-3. So yeah, so far I don't think we have explored that.
Okay.
And also, go ahead.
Say.
Just another kind of comment on the communication rate, that this is actually the step size that the FMU communicate with the host software. But you can also be able to define internal steps that the FMU can take if your equations is in a way that requires kind of a smaller time step. So you can use extra internal steps inside your FMU, but this communication step size is the time step that both tools are communicating.
Correct. Even on the Adams side, you could do something different. You could also scale up some of the outputs if needed, if you want to run it faster. But yeah, so for this particular workflow, it's set at 1E-3. I also saw one good question, which is like, are these Maplesim FMU parameters tunable inside Adams? And yes, they are. That is one very good advantage, where Saeed has essentially exposed some of these parameters for eco and sport, and they are tunable inside Adams. They can be toggled between, but you can't change the strategy. Maybe there is a way to also expose few additional parameters to change in Adams, but yes.
Right. Essentially, any parameters that you have associated with your model in Maplesim, as I kind of explained in the window for the FMU generation app, you can decide to keep them as they are without substituting them. So those parameters will be available to be tunable in the other tool.
Okay, thanks, Ed. There's well, there are a few more questions. I think we can take a few more. So there's a question about.
Yep.
Go ahead. Yeah, just.
The braking torque.
Shankar, go ahead.
The braking torque. There's a question: will the braking torque supplied by the motor in Maplesim is negative during braking? That is correct, Saeed. Right? As we go into braking or coasting, that the motor torque will slowly start going towards negative, right?
Right. That's true.
Yeah, and that's what we saw in some of the output plots in the Adams post-processor, that you could see that in the track event when we were braking or decelerating, you could see the motor torque go from positive to negative. And that's what's coming into Adams as well.
Yeah, that's true. Yeah.
And we can't run any closed loop event with this FMU. The current event was a smart driver event. So it's essentially a closed loop driving machine event that we were running within Adams. And if you're talking about exporting the Adams FMU into the Maplesim environment, then yeah, you could specify some other kind of speed trace or some target for the Adams model to follow.
So the chat window, Shankar, there's a question about solid, rigid versus flex bodies, I guess. So any thoughts? I know we didn't utilize it this time, but in your particular application, but any experiences or any comments on perhaps using the same application with flex bodies in there?
I think it would be useful to see how the forces actually transfer through a flex body, because then you'll get additional information on how the torques are reacting with a flexible body in Adams. So yes, definitely, I think to study the system in detail, especially the modes or some of the resonance or the NVH attributes of the model, it would be quite beneficial to run it with a flexible system as well.
Okay. Sorry, there's a question on the vehicle dynamics model used in the original Maplesim application. The question is besides the longitudinal dynamics model, do you have a lateral dynamics model as well? Hopefully I'm interpreting this question correctly.
So in the model that we saw, it was kind of for the first pass of the analysis. Actually, the longitudinal dynamics for the first pass can provide reasonable values for the amount of the load on the vehicle, so you'd be able to analyze your powertrain. But again, through this integration, you can use an Adams FMU. But still, if you want to do lateral dynamics or 3D vehicle dynamics, there are also libraries in Maplesim that you can build as you go, do more advanced vehicle dynamics and build your different components of your vehicle using, for example, multi-body library in Maplesim as well.
Okay, perfect. Perfect. Yeah, there are a few more questions. Shankar, I don't know if you want to take. I know you can see the Q&A. There are a few more Adams-related questions. Do you want to take any of them?
Yeah, how machine driver is. Yeah, so the machine driver, it can interface natively with the Maplesim FMU. We didn't make any big changes. So essentially, I mean, I can take this offline maybe. So Saurabh, you can email me and we could have a conversation on how this was set up. But essentially, we didn't make any big changes to the machine driver so that it's communicating with Maplesim. But yeah, we can take that offline as that might need some discussion. Yeah. I don't know if most of them are related. I think that might be a good place. Hemant, I don't know if you want to take any more interesting questions.
Yeah, we can. Yeah, as you mentioned, we could tackle the remaining offline.
Yep.
Shankar, and so yes, thanks Shankar, thanks Saeed. This is a great, very informative session, and thanks everyone who attended today. And look out for more announcements on similar electrified systems, vehicle systems related topics that we're going to present in the coming months. And with that, I'm going to close the session for today. And yeah, I just want to thank Saeed and Shankar both again for the very informative discussion.
Thank you. Thank you, Hemant. Thank you, Saeed.
Thanks everyone for joining and your time.